This lecture should be titled Fun and Games with Limits, since we are going to outline a bag of tricks and techniques for evaluating limits. If in fact the function f of x is continuous at x equal a, then there is no work involved in calculating the limit at a of f of x, since that limit is f of a. This covers all polynomials, and since we will prove later that all trig functions are continuous on their domains, they are covered. The caveat about domains means we don't make any claims about a limit involving a trig function at a point not in its domain. For sin x and cos x, this is no problem since they have the entire real line as domain. For the function tan x, remember the graph. From the graph, we can see that the domain is the real line with the following infinite set of points removed. That is, pi over 2 plus or minus all multiples of pi. So we can write, for example, that the limit as x tends to pi over 2 from below of tan x is plus infinity, and the limit as x tends to pi over 2 from above of tan x is minus infinity, and so on. However, if we went to study the limit of the product of x minus pi over 2 and tan x, as x goes to pi over 2 from the right, we need some more tools, because this is a product with one factor going to 0 and the other factor blowing up to plus infinity. To be certain that you understand that we need to be very careful about such limits, just consider the following three limits, which are very simple examples of a product going to 0 times infinity. The limit of x times 1 over x squared is just the limit of 1 over x as x goes to 0 from the right, and that's plus infinity. But the limit of x times 1 over x, which is also of the form 0 times infinity, is just the limit of 1, which is 1. And the limit, again as x goes from 0 to the right, of x squared times 1 over x is also the form 0 times infinity, and that's the limit of x, which is 0. Take a minute to examine these three examples, and then you modify the second one to get a limit of 3. Once you grasp these three examples, you understand that this type of limit needs special care. In fact, there are several situations in which special care is needed. In our casual notation, they are limits that end up looking like any of the following examples. Type 1, 0 over 0. For example, the limit as x goes to 0 of sin x over x. That is, both the numerator and the denominator go to 0. And we will prove eventually that this particular limit of sin x over x does exist and is equal to 1. And we're going to have to do some moderately difficult geometric and trigonometric analysis to prove it. Another type, type 2 we call it, is infinity over infinity. That is to say, something like the limit as x goes to infinity of log x divided by x. In this case, both the numerator and denominator are increasing and unbounded as x moves to the right. We will show that this particular limit does exist and is 0. But in general, we have to treat limits of this type one at a time, since anything can happen. In the spirit of the simple example I gave a few moments ago, you have the limit of x tends to infinity of x squared over x is of the form infinity over infinity and goes to infinity. The limit as x tends to infinity of 3x over x is of the form infinity over infinity and goes to 3. The limit as x goes to infinity of x over x squared is of the form infinity over infinity and goes to 0. Our third type is of the form 0 times infinity, which we discussed earlier. Our fourth type is of the form infinity minus infinity. For example, the limit as x tends to infinity of the difference between the square root of x plus 2 and the square root of x. Surprisingly, at least to me, this limit exists and is equal to 0. But don't think that you can just always assume that infinity minus infinity is 0. For example, we will show that the limit as x goes to infinity of the square root of x squared plus 2x minus the number x is a half. And in fact, we can create examples to show that infinity minus infinity is any number you want to specify. Our fifth form is limits that look like 0 to the 0. For example, the limit as x goes to 0 through positive values of x to the power x. In general, we reduce these to a limit of the form 0 times infinity by taking logs. Here's how this works. If you will accept that the natural log function is continuous on its domain, then we can assume that the limit of x to the x exists as a finite number cap L, and we take logarithms. So if the limit as x tends to 0 from the right of x to the x is cap L, then the log of that limit is the log of L. And you could interchange limit and log because the log function is continuous. So you conclude that the limit as x goes to 0 from the right of the logarithm of x to the x should be the logarithm of this limit L that we're trying to find. Now you can use the properties of the logarithm function to conclude that the limit as x goes to 0 from the right of x to the x is L, if and only if the limit as x goes to 0 from the right of x times log x is log L. So this means we can work on this last limit as x goes to 0 from the right of x times log x, and we will show that this limit is 0. And this is the logarithm of cap L, so the original limit cap L must be 1. Our sixth type of limit is infinity to the 0. For example, the limit as x goes to 0 through positive values of cosecant of x to the x power. Our seventh type is 1 to the infinity. For example, and we will use a sequence this time for a little variety, the limit as n tends to infinity of the quantity 1 plus 1 over n raised to the nth power. The term inside the parentheses, 1 plus 1 over n, goes to 1 as n tends to infinity, while the exponent n goes to infinity. This is a classic limit which we will eventually discuss in excruciating detail, and the value of this limit, surprisingly, is Euler's number e, the base of the natural logarithms. You should try a few values on your calculator, say n equals 10, 20, and 100, and compare what you get with the known decimal expansion of e. The sequence converges very slowly. Limits of type 6 and 7 are usually dealt with by either very special ad hoc methods or by taking logarithms as we did with type 5. After this exhaustive listing, you can be forgiven for thinking that these lectures are going to end up about as interesting as a course in corporate tax policy. Rest assured, we're going to stress general principles and ideas, not the memorization of a boring list of rules for dealing with a boring list of limit types. Let's start with rational functions, since polynomials are continuous everywhere and so offer no challenge. The only points at which a rational function is not continuous are points where the denominator is 0, so we focus on this type of situation. As an example, consider the limit as t tends to 1 of the 8th degree polynomial over a 6th degree polynomial as written. Both numerator and denominator vanish at t equal 1. The standard technique used on rational functions for which both numerator and denominator vanish at x equal a is to factor out all powers of t minus a from both numerator and denominator. This is straightforward in theory, but sometimes genuinely tough to carry out. In this case, both numerator and denominator vanish at t equal 1, so we look for a factor of t minus 1 in each. Be aware that the factor could be raised to a power. It turns out that in this case, the numerator factors as t minus 1 times a 7th degree polynomial, and the denominator factors as t minus 1 times a 5th degree polynomial. Because the statement limit as t goes to 1 specifically excludes the value t equal 1, we can cancel the common factor between numerator and denominator to get the equivalent limit of the ratio of the 7th degree polynomial to the 5th degree polynomial as t tends to 1. Neither of these vanish at t equal 1, so we can just evaluate them, and the limit turns out to be minus 5. About the only way we can dress up this kind of problem is to make the factorization harder, forcing you to use long division, for example. There's another class of limit which uses a sort of reverse factorization. Keep in mind for a moment the factorization a squared minus b squared is the product of a minus b with a plus b. Having tucked this factorization away in your memory, consider the limit as x tends to infinity of the square root of 2x plus 1 minus the square root of 2x minus 2. This has the formal structure of type 4 from our list, infinity minus infinity, which is just a shorthand way of saying that we are subtracting two expressions and each of them gets large and stays large without bound. The trick here is to let a be the square root of 2x plus 1 and b be the square root of 2x minus 2. And then use that factorization you tucked away in your memory. Now it's fair for you to comment that the given limit involves a minus b. In fact, it is exactly the limit of a minus b. But where is a plus b? The fact is it's not there. So we put it in without changing the expression by multiplying the given expression by 1 in the form of a plus b divided by a plus b. When we carry out this multiplication, use the factorization, getting a squared minus b squared on top, our limit becomes a limit as x tends to infinity of just the number 3 in the numerator divided by a sum of radicals, square root 2x plus 1 plus square root 2x minus 2. We notice that the numerator is now a constant while the denominator grows without bound, so the limit is 0. Here is a second example of this type of limit. Consider the limit as x tends to infinity of the square root of x squared plus 2x minus the number x. In this case, we do the same trick. We set a equal to x squared plus 2x, square root, and b equal to x, which is, of course, the square root of x squared. So the limit has the form lim x tends to infinity plus infinity of a minus b. Multiply the given limit by the ratio 1 equals a plus b over a plus b to get the expression that we've written down, which simplifies then using our factorization to a numerator with just a squared minus b squared. That numerator simplifies to 2x and the limit becomes 1. Now the fact that that limit is 1 does need some explaining, and in fact introduces another very important technique for handling any ratio of functions involving powers and roots of x as x goes to plus or minus infinity. The principle that I used is factor out the highest power of x which appears in the numerator and do the same for the denominator. Let's do a simple example before I justify the last formula. Consider the limit of radical x squared plus 1 plus 2 divided by x cubed plus 2 to the 1/3. The highest power of x in the numerator is x squared, and we factor that completely out. In the denominator we see an x cubed, and we factor that completely out, paying attention to the change in power as we pull factors through roots. We end up with the limit as x tends to infinity of x on the top times an expression in brackets that involves the number 1 and some other terms which are divided by powers of x. In the denominator, we end up with an x factored out times the number 1 plus a term 2 over x cubed. Now notice that any term with the denominator involving a power of x goes to 0 as x goes to infinity. In addition, the initial factor of x in the numerator cancels with the initial factor of x in the denominator. So we cancel them, and we end up with a limit of 1. Now let's attack our original more difficult limit, which was the limit as x tends to infinity, when simplified, of 2x divided by, and then in the denominator we factor the x squared out of the square root, so it becomes an x times the square root of 1 plus 2 over x, and then cancel that with the x in the numerator. So we end up with a limit of 2 over radical 1 plus 2x plus 1, and we get a limit of 1. The reverse factorization idea can be applied to higher degree polynomials. Keep in mind, for example, that if you have a minus b, you can multiply it by a squared plus ab plus b squared and get a difference of cubes, a cubed minus b cubed. So if you have a limit like the limit as x tends to infinity of the cube root of 2x squared plus x minus the cube root of 2x squared minus 2x, then you can let a be that first cube root and b be that second one. Then multiply the original expression in the limit by the ratio of a squared plus ab plus b squared to itself to get a very complicated looking expression that simplifies because the numerator becomes a cubed minus b cubed, which clears the cube roots. In fact, the numerator simplifies to 3x. And when you pull the factor x out of the denominator trick, you end up with x to the 4/3 in the denominator. So our limit must be 0, since that x to the 4/3 in the denominator will dominate the x in the numerator. Well, as you can see, the use of reverse factoring is messy, but it is effective. We will look at two more important limits, both of which require special methods. The first is the fact that the limit as n tends to infinity of n divided by e to the nth is 0, where e is Euler's number. In fact, you can take any power of n. The limit as n tends to infinity of n to the k over e to the n is 0 for any fixed power n to the k. In fact, the exponential function grows more rapidly than any polynomial. For this lecture, we will focus on the sequence, since once we have the power of the calculus at our disposal, the stronger results will be easy to prove. To show that the limit as n tends to infinity of n divided by e to the power n is 0, we're going to need an improvement of an inequality, namely Bernoulli's inequality, which we established in an earlier lecture. In fact, we may as well bite the bullet and establish a much stronger result known as the binomial expansion, which gives us Bernoulli's inequality and all possible improvements of Bernoulli's inequality. In a nutshell, the binomial expansion theorem states that the sum of a and b, a plus b, raised to the nth power, can be expressed as a sum involving products of powers of a and b. The powers are a to the n minus k times b to the k. Notice that the two powers always add to n. And the coefficient of each of these products, a to the n minus k times b to the k, are called binomial coefficients. And I've written them out in the formula so you can see exactly what they look like. The formula is quite intimidating in both the condensed summation notation and when written out, but in fact it has a beautiful symmetry which most students have seen in high school as Pascal's triangle. Before we talk about the Pascal triangle, let's have a close look at the statement of the theorem. The summation notation version uses a shorthand notation for the numerical coefficient of each term. If n and k are natural numbers, or 0, with n larger than or equal to k, then the symbol given is called a binomial coefficient, and it's defined in terms of factorials. We will call it b of nk. In plain English, j factorial is the product of all natural numbers from 1 to j. Keep in mind that 0 factorial is 1. Then the binomial coefficients are defined by b of nk equals n factorial divided by the product of k factorial and n minus k factorial. And that simplifies to, in the numerator, the product of n with n minus 1 with n minus 2 down to n minus k plus 1, and in the denominator k factorial. Do a little calculating to show that binomial coefficient nn, b of nn, and binomial coefficient b of n0 are both 1. Show that binomial coefficient b of n1 and b of n minus 1 are both n. Now, when we gave the formula for defining the binomial coefficients, the second formula looks a little bit confusing. To get that formula, first recognize that n factorial is the product of all the numbers up to n and does contain the smaller product n minus k factorial, which is the product of all the numbers from 1 to n minus k. So from the expression n factorial divided by n minus k factorial, you can cancel n minus k factorial from both the numerator and denominator, leaving that strange residue in the numerator and the term k factorial in the denominator. To increase your familiarity with the definition of b and k, let's calculate a few specific binomial coefficients. b10 is 1, b11 is 1. Now let's go to n equal 2. b20, well, that's 2 factorial over 2 factorial and 0 factorial. That's 1. b of 21 is 2 factorial over 1 factorial, 1 factorial, and that's 2, and so on. Using our binomial expansion theorem and these calculators, we can write b10 is 1, b11 is 1, so a plus b to the first power should be 1 times a plus 1 times b, and trivially it is. Now go to the case n equals 2. According to the binomial expansion, the three binomial coefficients in order for n equal 2 are 1, 2, and 1. So a plus b quantity squared should be 1 times a squared plus 2 times ab plus 1 times b squared, which it is. Now go to n equal 3, where we calculated the binomial coefficients to be respectively 1, 3, 3, 1. And this means that a plus b quantity cubed should be 1 times a cubed plus 3 times a squared b plus 3 times ab squared plus b cubed. If we arrange the binomial coefficients in order, one line for each value of n, we get the famous Pascal triangle, which exhibits them. Just to put a proper vertex at the top of the triangle, it is customary to have a row for n equals 0 with binomial coefficient 1. Each entry in a row is got by adding the two entries just above it on either side. So, however you wish to calculate the coefficients, either by the binomial expansion theorem or by the Pascal triangle, you can now expand a plus b to the nth for any natural number n. Of course, we have to prove that this formula is correct, but let's delay that for a while so we can focus on limits. In fact, let's return to the limit as n tends to infinity of n divided by e to the n. Given the binomial expansion, we know that e to the power n is 2.718 ... raised to the nth power. And that's 1 plus 1.718 ... raised to the nth power. And that's a plus b to the nth, with a equal to 1 and b equal to that decimal expansion. And so you get 1 to the nth plus n times 1.718 and so on, plus the next binomial coefficient, which is n times n minus 1 over 2 factorial, times that 1.718 thing squared, and so on. Now what we're going to do is throw away everything else in that expansion, all the other terms, and just keep those first three terms. Doing so, we get a smaller number. We've thrown away a lot of positive numbers. So e to the n is greater than 1 plus n times 1.718 dot 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 plus n times n minus 1 over 2 factorial times the square of that 1.718 number. This is the extension of Bernoulli's inequality that we need. Just to recall, Bernoulli's inequality stated that for a positive number a, 1 plus a to the nth is bigger than 1 plus na. What we have just shown using the binomial expansion is that 1 plus a to the nth is bigger than 1 plus na plus n times n minus 1 over 2 times a squared. Of course, we could have kept the cubic term and so on to get an infinite string of inequalities, but this will do for our purpose. So if we let the letter a represent the decimal 1.718 dot dot, then we can use our inequality to write that n divided by e to the nth power is first of all positive, and secondly less than n divided by 1 plus na plus nn minus 1 over 2 times a squared, since if you use a smaller denominator, you get a bigger fraction. Now we factor the largest power of n from that denominator, and you get that n over e to the nth is greater than 0 and simultaneously less than 1 over n times an expression that obviously converges to 1 as n tends to infinity. Then it is clear from the squeeze theorem that the limit as n tends to infinity of n over e to the n is 0. You should also take a moment to notice that if we were dealing with the limit of n squared over e to the n as n tends to infinity, then we could just use the inequality you get by taking 4 terms of the binomial expansion and throwing the rest away. That is, we would write down 1 plus a to the nth power is bigger than, and then write out those 4 terms through the cubic term in a, and that would also involve an n cubed in the numerator of the coefficient of a. And then you would have that 0 is less than n squared over e to the n, of course, and that in turn is less than n squared over that cubic polynomial. The highest power of n in the denominator is now n cubed, while the highest power in the numerator is n squared. So the limit of this last fraction will be 0, and again, by the squeeze theorem, the limit of n squared over e to the n is 0. And now it is clear we can deal with any power of n in the numerator by taking enough terms in the binomial expansion of 1 plus a to the power n, which is how one proves that the limit as n tends to infinity of n to the k over e to the n is 0 for any real number k. The same is true for the function x to the k over e to the x as x goes to infinity. We should take a minute to understand how this demonstrates the awesome growth of the exponential function. If you consider the function p of x equal x to the 100th power over e to the x, we have just proved the limit of this function as x goes to infinity is 0. A tabulation of the values of the numerator and denominator, and then the function p of x, is instructive. When x is 2, x to the 100th is roughly 10 to the 30th, and e to the x is 7. And the value of p of x is 1.71 times 10 to the 29th. When x is 10, x to the 100th is 10 to the 100th, e to the x is 2.2 times 10 to the 4th, and p of x is 4.5 times 10 to the 95th power. When x is 100, x to the 100th power is 10 raised to the 200th power, e to the x is 2.688 times 10 to the 43rd power, and the ratio p of x is 3.7 times 10 to the 156th power. As you can see, this hardly looks like a function which is going to 0. However, by x equal 10 to the 4th, the exponential is beginning to take charge. For x equal 10 to the 4th, x to the 100th is 10 to the 400th power. E to the power 10 to the 4th is 8.81 times 10 to the power 4,342. And p of x is 1.135 times 10 to the minus 4341. This is the reason that bacterial growth can be so deadly in the long term. The growth of a bacterial population is approximately exponential as long as the supply of nutrients is adequate. This example, to show that the limit of x to the k over e to the x is 0, was very long and involved, and in fact we only gave a complete proof for the sequential version. Don't be discouraged if you find it hard to assimilate on the first try. It took some very brilliant mathematicians several decades to figure out what was going on. If you can get the general idea at this stage, that's fine. Also, you should notice that using calculators on functions like this requires a lot of care. Just try graphing x to the 100th over e to the x from x equals 0 to x equals 1000. This limit also tells us something about logarithms. If you define x to be the logarithm of t, then x going to infinity corresponds to t going to infinity. And furthermore, e to the x is just e to the log t, which is just t. So the function x over e to the x becomes a new function of t, namely log t over t. And what our work has shown is that the limit as t tends to infinity of log t over t is 0. In other words, log t is weaker than the linear function f of t equal t as t tends to infinity. After all that work on the limit of x to the k over e to the x, you would think we would rest a bit, but I want to finish by looking at a completely different type of limit. One of the most important limits we will need in the future is the limit as x tends to 0 of sine x over x, and that limit is 1. When we have limits involving trig functions, we usually have to think in terms of geometry and trigonometry, a completely different approach from limits involving the exponential and log functions. The complete treatment of this limit is presented in the notes, so in this lecture I will just try to motivate the approach used and outline the key ideas involved. If we're going to compare an angle x with the value of sine of x, we need a picture of the circle of radius 1 with x and sine x identified with objects on this circle. Since both sine x and x are odd functions, their ratio is even, and we need only consider the limit from the right. From the sketch, we can identify the angle x as the arc length of the part of the circle subtended by the angle. The value of sine x, which is side opposite over hypotenuse, is just the height, that is the y-coordinate of the point C. Notice that the point D has x-coordinate 1, and therefore the y-coordinate of the point D is just tan x, side opposite over side adjacent. You should verify each of these observations carefully. They are fundamental. It is clear that the length of EC equals sine x is less than the length of the chord or straight line between C and A, since that chord is the hypotenuse of a right triangle with side EC. The chord, in turn, is the shortest distance between A and C, so the arc length x, which reaches from A to C along the circle, is greater than the length of the chord. What you get from all of this is that sine x is less than the length of the chord between A and C, which is less than x. Dividing by x, we get that sine x over x is less than 1. So we have bounded sine x above by a constant function with limit 1 as x goes to 0. If we can bound sine x over x from below by something that converges to a limit of 1 as x goes to 0, then we can apply the squeeze theorem and we're done. From the picture, it appears that the obvious inequality is x is less than the length of the straight line AD, which is tan x. If this is true, and remember the pictures suggest, they don't prove, then we can write x less than sine x over cos x, and again with a little division we get cos x less than sine x over x. Since, at least intuitively, the limit as x goes to 0 of cos x is 1, we have a lower bound with limit 1 and we are done. The careful argument that in fact x is smaller than tan x is a nice exercise in elementary geometry and is given in the notes. So this completes our introduction to the world of difficult limits. As we go through the course, we will develop some powerful methods to assist us, and we are going to be very grateful to get some additional tools and reduce the workload. To finish off, I will outline a proof of the binomial expansion theorem, which, as is so often the case, uses induction. If you have found this lecture a bit heavy, I would recommend you just accept the binomial expansion for now and focus on limits. Here is a statement of the theorem. Quantity a plus b raised to the nth power is the sum k equals 0 to n of b of nk times the product a to the n minus k times b to the k. First, for n equal 1 and 2, the theorem states the following. A plus b to the first power is a plus b. Good. A plus b quantity squared is b2 0 a squared b to the 0 plus b2 1 a first power b first power plus b2 2 a to the 0 b squared. And when you write that out, it's just a squared plus 2ab plus b squared. So far, so good. Now comes the messy part. Assume that the theorem is valid for a particular value of n. And let's call the formula a. A plus b to the nth is assumed to be equal to the given binomial expansion. We have to show that we can start with this formula a and show that the formula for n plus 1 follows from it. That is, we want to arrive at the formula b. A plus b to the n plus 1 is the sum from k equals 0 to n plus 1 of binomial coefficient n plus 1 k times the product a to the n plus 1 minus k, b to the k. Notice how the notation saves us a lot of writing. The obvious way to get from a to b is to multiply both sides of a by a plus b. And then you get formula c. A plus b to the n plus 1 is the term a plus b times the sum bnk a to the n minus k b to the k. Now we have to show that the right-hand side of this last expression c is equal to the right-hand side of b. Let's start small. Do the coefficients of a to the n plus 1 match? On the right side of b, there is a single term containing a to the n plus 1. It's just b of n plus 1, 0 times a to the power n plus 1, and that's just 1 times a to the n plus 1. On the right side of c, you get a single term involving a to the n plus 1, namely a times bn0 times a to the n. bn0 is 1, so again we get 1 times a to the n plus 1. Now let's check the next term, a to the nth power, b to the first power. On the right side of b, this term is bn plus 1, 1, a to the nth power b. And when you calculate that, that's just n plus 1, a to the n, b. On the right side of c, and you will have to think a little here, there are two terms with a to the n, b, namely a times bn1 a to the n minus 1b plus b times bn0 a to the n. Now you can collect the two a to the nb terms and add the two binomial coefficients bn1 plus bn0, and when you work it out you get n plus 1 a to the nb, exactly what we wanted. This last argument gives the foundation for the rest of our proof. Let's compare the terms involving a to the n minus 1b squared. From b, the coefficient of a to the n minus 1b squared is bn plus 1, 2 times a to the power n minus 1 times b squared. And when you clean that up, it's just n times n plus 1 divided by 2 times a to the n minus 1 b squared. From c, you have two terms again, a times bn2 times a to the n minus 2b squared, plus b times binomial coefficient bn1 times a to the n minus 1b. When you put those together, you're adding the two binomial coefficients bn2 and bn1. And when you clean that up, you get n times n plus 1 divided by 2 times a to the n minus 1b squared, exactly what you got from the formula b. In general, for the term in a to the n plus 1 minus k b to the k, you have from b the term b, binomial coefficient b, n plus 1k, times a to the n plus 1 minus k times b to the k. And when you clean that up, you get a product with coefficient with numerator n plus 1 times n minus 1 down to n minus k plus 2 over k factorial times a to the n plus 1 minus k b to the k. It's not pretty, but it's accurate. From C, there are, as usual, exactly two terms, namely a times binomial coefficient bnk, a to the n minus k b to the k, and b times binomial coefficient bnk minus 1, a to the n minus quantity k minus 1 times b to the k. And when you put that together, you get a sum of two binomial coefficients, bnk and bnk minus 1, with the product a to the n plus 1 minus k times b to the k factored out. You write out these two binomial coefficients, and they are a bit messy. You put them over a common denominator of k factorial, and you get exactly the expression that you got from formula b.